Hello, everyone. I'm sorry that I cannot attend the meeting in person with you guys and discuss the questions with you in class. So the alternative way that I suggest that I choose is to present this presentation online via video, and hope you guys can enjoy and understand the concept provided by our group. The first we are going to talk about is just the more about the case surface, which is the double refraction. So starting from the Snell's law, it's quite the same concept. And in our case, we suggest in the air, so N1 equals to 1 in this case. Of course, here is the theta 1. So, as what we have learned before, you may consider that there's only one wave propagate. But since we are considering an isotropic media, you may have different refractive index along different direction. And taking the uniaxial as an example, where uniaxial is defined as N1 equals to N2, but not equals to N3 in these cases. We would define it to have a no ordinary and extraordinary refractive, where ordinary is just the case surface of it is literally a surface, which is identical to the isotropic case. However, for uniaxial, it has extra solution, which is the ellipse. And here is the extraordinary refractive index comes from. Thus, with a given direction, you may have found different two solutions. And the optic axis here means that consider the case surface of the uniaxial. Along this direction, you may only suffer from one refractive index instead of two. Thus, this axis is called optic axis. So back to our Snell's law. Since we have experienced two different normal modes corresponding to two refractive index, the Snell's law remains the same, but we would plug in two different normal modes value inside the refractive index here, and with it corresponds with different theta, with different angle of it. And that's it for the chapter 2. So chapter 2 is just about a case surface, where case surface is given a temporal mode, it may correspond to several spatial mode. That's the case surface. And now we're at all. And just a quick reminder that this can also be called birefringence for your reference. So next, now we're going to jump into chapter 3, where acoustic optics take place. So consider a material and consider its place in a vacuum. Consider a wave located just above the surface. We may expect it to just go over it. However, if we have an acoustic wave, this may lead to refractance. So the acoustic wave is just like a grating, right? A grating where you have an incident and you may have refractive. And usually, we consider the Doppler effect to be very small in this case. So, in order for us to still see the light without loss, theoretically, we assume the path difference to be m, to be integer multiple of wavelength. And further derivation is that consider this length, and then you will find that theta b this angle plus this angle equals to 2 over pi. And this angle plus this angle also equals to this, which means this is theta b. Thus, we may found that the red line here corresponding to sine theta b. And the total path difference is 2 times of it. Thus, we come into this kind of conclusion. And besides the phase, you may also need to take the momentum, the energy into consideration. And here we may take into some concept about quantum physics, which is about a phonon. A phonon will cause the momentum and energy here into this kind of relationship. Actually, this is special to kind of this way, where you have an eye and you have a refractive. And you just move it here, so you will form a closed triangle. And similarly, you just switch it, you make that a minus phonon. For energy conservation, you need to have the omega to be in this kind of relationship. However, usually this is quite small, so compared to this one, so it's kind of approximate to it. And if this case happens, the Bragg condition comes to take place. And you may be curious about that. Under this condition, you may only have one of them. However, this suggests that different theta b may correspond to different they're an integer multiple of it. However, usually we will only consider n equals to 1, 1 plus minus 1. Because as m goes larger, theta b goes larger, and the electric field goes lower, which means the intensity goes lower. And that's not what we are interested about. Thus, usually we consider n equals to 1 the case. So now, I think this is the basic concept about it, but just to provide you another way to understand index modulation under this acoustic wave, we introduce the concept of a tension strain, divided in this way and a vivid picture aside it. Taken the oscillation frequency and the propagation direction into consideration, you may form into this kind of form where the intensity have this kind of interpretation. Take the unit into consideration. This is actually V3 SO3. Note the S0 here is actually unitless because it's M over M. So we may omit it temporarily. And this term gives the energy. Thus, only times V left, which gives, and this is the power. So actually it's the area per power, the power per area. Listed here. So just take into electro-optics into consideration. You may find a refractive index is related to strain as this kind of form. So to sum up, you may express the refractive index according to the x and t into this kind of form, where p is the photoelastic constant. And from the above, we may find that the delta n is equal to this, where m is kind of depend on the material, because as you can see here, law is the density of the material. So just as the light has diffraction, so does the acoustic wave, which is sound wave, in more easily known. name. The half angle of diffraction comes with the same energy condition, where we just substitute lambda and d equals to the diameter of the wave. It's just the same, so it's just energy of it. And speaking of the propagation diffraction, some people may think of scattering. That what if I have multiple incident propagation vector scattering? It's kind of possible. However, it's only allowed for board acoustic angular spectrum because you need to have the angular, the phonon that makes you obey the energy and momentum conservation. So if you are only in a single acoustic wave vector, that will not be the case. So I think I kind of said all of it. So just to special mention, that if we have instead theta is much smaller than theta, then it means that only one wavelength along certain direction matches the Bragg condition. So we only have this mode. But if we have opposite, then the scattering mode is acceptable. And okay, so now I would like to briefly sum up. So for chapter 2, it's all about the K-surface. What is K-surface? The K-surface is about given a temporal mode omega, you may draw all the possible spatial mode K on the surface, where given propagation direction will lead to two different normal modes. And it may be used in double refraction, the concept of it. And the example we use here is the uniaxial. As for the acoustic wave, there are several acoustic wave, it may act as grating. But I think I forgot to mention here that usually it may also have Gaussian behavior, and that's why we're writing this way. And we call Gaussian that when it's really close to here, it's approximate to a plane wave. So keep continue. In this case, we usually consider that the Doppler effect to be quite small. And for all the grating effect, you need to, for the wave to not experience the loss, we hope the path difference to be the integer multiple of the wave length. And also you need to take into the momentum energy conservation all into consideration where quantum physics takes a little place, especially about the phonon. And just as light, the acoustic wave also diffracts. And the condition of it is just quite the analogy of it, where you just substitute the lambda and substitute the diameter of the light to it, having a corresponding value, coming the counterpart of it of the sound wave, just gives you the condition. And I think that's all for me to sum up that what we have learned. And next slide provided by Wang Fly is all about the vector analysis, scalar theory, and that's more about math. Hope you guys enjoy this lecture. And if you have any questions, please tell me. Thank you.